I'm a happy camper again. I should have said that before. Let's continue with chapter 7, talking about consistency replication. Warning. This is a difficult chapter. What I'll be doing is I'll start today by talking a bit about consistency replication, but you're instantly going to get a hard time. I'm going to talk about data center consistency and most likely also client-centric consistency. Most of you will find this, data center consistency, difficult. I will do my best to explain it in a simple way, but it is more of getting into a mindset, and then you'll see what's actually going on. But it's kind of difficult, actually. Okay, so be prepared, be awake. Here we go. Okay. What I'll be doing is I'll be talking about lots of replication. And what I told you a couple of times is when you replicate, you will instantly have a consistency problem. Now, consistency means that your copies are not the same, okay? And what people have been wondering about is, can we actually play with this consistency in order to make sure that even if you have lots of copies, you can still have very reasonable performance? So what I'll be doing is the following. Okay, this is basically the main issue. You want to keep things consistent. You need to ensure that all conflicting operations are carried out in the same order everywhere. And we already saw this with the replicated database. What's the conflicting operation? If you take a look at the world of transactions, you have read-write conflicts and write-write conflicts. I'm more interested in the write-write conflicts. If you handle the read-write conflicts in a decent way, you can kind of circumvent some problems. The write-write ones are really nasty because it always leads to conflict resolution, which is which is in general application dependent. By the way, people are now working on this more than, again, 10 years ago because of all these multi-core processors. So you want to have lots of parallelism on your processor. And if you can have the right type of data structures, you can actually diminish the number of write-write conflicts. Okay. So these are the things that you want to avoid or that you need to handle. And the whole idea is that in order to still have a decent performance, you need to make sure that you can actually tolerate, to a certain extent, inconsistencies, but then I need to talk about what inconsistencies really is. So what we want to do is you want to weaken the consistency requirements so that hopefully global synchronization can be kept to a minimum. Okay. This is the picture I want you to keep in mind. Okay? This just got to burn this into your brain cells. I'll be talking about, now I'm going to talk about data-centric consistency models. This is the abstract thing. It's a contract between a distributed data store and processes in which the data store specifies precisely what the results of read and write operations will be in the presence of concurrency. So that means just you have multiple processes acting on the same data. This is the model that I want you to keep in mind. I have a bunch of processes. In practice, for the type of data center consistency models I'll be discussing, these are between 3 to 32 processes, not hundreds. Okay, for hundreds it simply doesn't scale. Exceptions to the rule. Each of these processes operates on a local storage, be it main memory, be it its disk. I couldn't care less, it's local storage. However, from the outside, these local storages together seem to be one big shared storage, okay, with one big single addressing scheme. Just to give you an idea, for those, well, most of you have taken courses on computer architecture. Imagine that you would have a big distributed system consisting of a bunch of PCs, why not, ordinary personal computers, but I applied a trick. I simply stacked all the memories of these personal computers and mapped them into one big virtual address space. Okay? And what you can then imagine is that you can have one single addressing scheme for the entire memory, but as soon, and let's keep it simple, let's say I have two computers, and you've stacked the memory into a lower part and a higher part. If I'm the computer who has the lower part of memory physically allocated to it, and I address something in the higher part, then you would get a memory fault. That means your request would go to the operating system. It would discover, oh, that's not over here, that's at its neighbor, where it passes the request to the operating system saying, okay, yeah, that's my part of the show, and it will be operating over there. Now, the important observation is that from my perspective, I'll be operating on local memory. Okay? And the operating system will make sure that my request is passed over to the other part of memory. Now, that's the model. So I'm operating on local storage, and I have a distributed system, middleware, that what it does is if it sees an update over here, will make sure that the update is propagated to the other guys as well. Okay? That's the model you should take in mind. Now, the first thing I'm going to do is talk about continuous consistency. The whole idea was, the whole idea of data consistency, data center consistency, comes from basically the shared memory model that I just described. How can we make sure that concurrent access to the same memory can be handled decently? Because you can imagine if somebody else writes to that same location in high memory, it is in conflict with possibly writes from another guy over here, okay? And that leads to ordering requirements on operations. But other people have also thought, well, you know, before doing that, you can also talk about a degree of consistency. And the degree to which you let conflicting operations be out of order is one degree of consistency. But there are at least two other dimensions that you should take in mind. The numerical value of something and time, the staleness of an operation. And what I just said was basically the order in which update operations are performed. I'll talk about this separately. The numerical value is very simple. My example that I always give is, take a look at stock markets. Okay? What I could specify, if you take a look at the stock market system or a stock system, there are lots of data streams coming into a system, and those data streams go over to this system over there as well as that system over there. And what's very crucial in the stock market is that you act on time and basically on the same data. Okay? So what you could say is that, okay, I want my algorithm to buy or sell stocks to be automatically triggered when I see a difference in a specific stock value of more than 0.1%, just to give you an idea. Okay? So that could be a relative deviation from its current numerical value. Or you could say, no, if that stock goes up by, let's say, 50 cents, that's when I want to be notified. And what you're basically saying is that your copy of the value of the stock may deviate from a value somewhere else up to 50 cents or 0.01%. Yes?
It does require or generates an enormous amount of traffic.
This requires a lot of control traffic, yes. I'll come to that, I think, tomorrow or on Thursday. It's a tough problem, by the way. For now, I just want to look at the consistency requirements. So what I'm saying here is that you can formulate consistency in terms of deviation in the numerical value. You could also do this for staleness. The web is good at this. I will simply permit that certain pages are 5 minutes still. Okay? And to keep it simple, if I can give you this view on the world, you're happy. If you don't even know that an update has been done, but you can't even see those things, and there's no backdoor channel to say, oh, whoa, didn't you see this? You're a happy camper. You couldn't care less. And if I can tolerate, let's say, a 5-minute delay, whoa, that may save me sending a lot of updates in the meantime, because I can now aggregate the updates and send them in one go to this specific web cache, for example. Now, a crucial thing here is the consistency unit, the CONIT. What are we talking about? Are we talking about a web page? Are we talking about a record in a database? Are we talking about an entire table in a database? So like I just said, in the case of the stock market, I could be saying, well, a consistency unit is a single stock value. It could also be a set of stocks, okay? And what you can then do is you can talk about the consistency over that consistency unit. And then you get this awkward picture. And every year I try to explain this, I explain it. And every year I will tell you, well, for the third edition, this thing has to be improved. Okay. But nevertheless, I'm going to tell you what's here. I have two replicas. And I'm assuming that each replica holds a copy of the variable x and y, and both variables are initialized to 0. Okay? And what these replicas do is they operate on their local copy, and when they operate on their local copy, they send the operation that they just performed to this other replica. And what you can then have is that you can have a series of operations, one after the other, here at replica A, and a series of operations at replica B. And if we take a look at this one over here, replica A has received an operation with this timestamp 5, x becomes x plus 2. And another one from A, I should say, y becomes y plus 2, and another one, y becomes y plus 1, etc. These are from A, this one came from B. B has performed two operations, x becomes x plus 2, by the way, has also been moved over there, and there's this one over here, y becomes y plus 5, but this thing is only still in its local queue. It's still pending to be made permanently, okay? So, what happens then is that every operation should also be sent to the other replica. When you send an operation to the other replica, it gets, how should I put this? It's being placed in a queue, and then the operation will eventually be executed on your local variables. Okay? Now, I made this one gray to illustrate that this operation has been executed and cannot be rolled back. It's been made permanent. These ones, hey, they still are in the queue. If I was an application, I could take a look at what the effects are of these operations, and then in the end I would find that x appears to be 6 and y appears to be 3. So these two values come from executing these 4 operations in this sequence. Okay? Likewise, if you take a look at what's happening at replica B, the seeming values of x is 2 and y is 5 come from the fact that you execute these two operations one after the other. So far, so good? Now, what I want to do is I want to define a consistency over these two replicas. Are these two consistent or not? Well, what I'm doing is every replica will maintain a vector clock. And the vector clock says the known time at A and the known time at B. Okay? So in this case, if you take a look at the vector clock at A, it says, well, my last operation over here was 14, so my time is 15. Okay? And the last thing I saw from B was 5, so at least I know that it should be 5 over there. Likewise, if you take a look at the vector clock at B, it says, well, I haven't seen anything from A, so I can only assume that its clock over there is 0. By the way, I've already advanced my clock at least to 10 plus 1 is 11. So that's an easy one. Okay, in this case, B had sent this operation to A, which came over here in this queue, okay? And A has made this operation permanent. It cannot be rolled back. Okay, now it becomes a bit more difficult. Now, again, the consistency unit, the conent contains two variables, x and y. Okay? A has 3 pending operations, these 3. And B has 2 pending operations. And in this case, this is only by definition of what I found interesting, and I is the designer of this system. It says, well, I have an order deviation of 3 at A, and I have an order deviation of 2 at B. And a pending operation means an operation that is still in the queue and has not been yet made permanent. Okay? Now, A has missed 1 operation from B, yielding a max diff of 5 units. Now, this is always the nasty part, and I'm not quite sure whether I'm willing to explain this. I should explain this. A has missed only this operation from B, right? And what I do is in my numerical deviation is say, okay, I'll just record the fact that A has missed this 1 operation. Now, the maximal diff, that's kind of difficult. Basically, what I'm trying to do over here in this numerical deviation is say, okay, how many operations have you missed? And how far are you maximally behind the other one? In this case, I'm looking at x as well as y. And what you'll then find is that A is 5 units, which in this case I think is the maximum of y behind B. Now this is always the part, it's explained in the book, but I don't want you to remember this too hard because the example is actually not good enough. Let me give you another definition of numerical deviation. One could be, listen, I'm not going to look at x or y, I'm just going to take a look at only x. I think that's the way how I should improve this example. And I'm going to say, just like in the case of my stock market, you are allowed to deviate at most so many units from the other replica. And in this case, this maximum deviation is defined over the maximum diff with respect to x and y. That's the confusing part. Okay? So if you just take this example of one variable, x, then you say, okay, how much can you deviate from the other replica? Let's say 5 units at most. Now, the thing you need to realize here is that what I'm specifying are different issues of consistency, notably the order deviation and the numerical deviation. I could throw in other criteria for deviating, and the trick is that you now have metrics by which you can measure how far you are off with respect to the other replica. And the question is, how much will you tolerate? And tomorrow or Thursday, I will take a look at an implementation by which you say, okay, if I can tolerate at most a diff of so many units, then the whole thing starts to work as soon as you have a chance of coming close to that maximum deviation. Those are the control packages you just mentioned. This is just a specification of where you are, and tied to the specification you can say, I want to tolerate just as much as this. Okay? What I would like you to remember about this example is only the principle. I'm not going to ask any nasty questions about consistency units. But I do want you to understand what a consistency unit is and what types of consistency you could associate with a consistency unit. That's it. The example, in hindsight, I'm not very happy with. Okay. That was that. Now I really want you to pay attention. What time are we doing? Yes. You just saw me stumble a bit about the ordering issue. And I did this on purpose because in the consistency unit, in that part of the theory where people have been thinking of, I think a better job has been done by people who've been working in distributed shared memories. You really have to realize that people started to build hardware and they thought to themselves, I can't synchronize everything because that's just going to lower the performance of my really nifty parallel machine without shared memory, but having a distributed shared memory. So let me start defining all kinds of data-centric consistency models that have everything to do with the ordering of operations. Now, this is the one, you'll be surprised, this is the one that we're all familiar with. Okay? And just read this definition. A sequentially consistent system is one in which the result of any execution is the same as if the operations of all processes were executed in some sequential order, and the operations of each individual process appear in this sequence in the order specified by its program. Yeah, sure. What is this? It sounds very logical, yeah. But my claim is, you know what I'm talking about. You know what this is. Which one?
It's atomic process.
No, it's not. Well, you're getting close. It's an atomic process, but it's more. Yeah? What? No, not transparency in time. Transactions. Let's use the word transaction. For those, how many of you followed a course on databases? Enough. Watch this. The result of any execution of a collection of transactions is the same as if the read and write operations contained in an individual transaction were executed in some sequential order, and the operations of each transaction, the read and write operations within each transaction, appear in the sequence, in the order, in the sequence specified by that transaction. So what you're saying is that if I take a look at the individual transaction in terms of read and write operations, I will obey those ordering of read and write operations within a transaction. Hooray! If I take a look at a collection of transactions that are supposed to be executed concurrently, then the end result can be explained by a situation as if I first executed transaction 1, then 3, then 5, then 4, then 6, then 8, then 2, etc. As long as the end result can be explained by one of those orders, then I'm a happy camper. That's sequential consistency. So this is just transactional stuff. And indeed, you formulate in terms of read and write operations. Now, before we take a break, take a look at this scheme. What I'm doing over here is I'm having time go from left to right. And I have 4 processes over here. And here's something that you need to get used to. This is absolute time. So if I'm an observer, I see the following. I see a write operation on variable x, and I'm writing a to x. Later, I see process 2 write b to x. And even later, I see process 3 first read b from x, and then read a from x. And process 4 reads b, and then a. I'm saying to myself, I'm a happy camper because this is sequentially consistent. This makes perfect sense to me. No? You haven't? Oh.
I didn't see where you're going with it.
Wait until if there's a time in your life that you become a father, it's bye-bye sleep. No matter what age your kids ever will be. But apart from that, why does this make sense? Why? Okay, to many of you this doesn't make sense because what I said is, look, process 1 first wrote A, and then process 2 later wrote B, and now you're telling me that's okay that process 3 first reads B and then A? as well as process 4? I'm saying yes. Because we have no time. We're only interested in consistent ordering. And from a systems perspective, these are two concurrent write operations. So I don't care who goes first as long as I have the same ordering everywhere. And fortunately, this is exactly what I'm seeing. And apparently, what the middleware was doing was moving the second, quote-unquote, write operation first to all the replicas, and then notice, oh, yes, process 1 also wrote something. Good. Let me now forward that to the others. And now I'm seeing that everybody's reading exactly the same thing. Namely, the end result is A. That's what you would expect in a parallel program where you have not protected your variables by means of locks. You would expect garbage, but you would expect the same garbage everywhere, right? This one is not sequentially consistent because I have A being written to X by P1, then P2 writes B to X, and then the middleware screwed up because it said, well, let me then propagate B to P3 and then A, but for P4 I'll first propagate A and then B. Middleware, you didn't do your job right. Because in this case, the end result of P3 and P4 will be different. That is not sequentially consistent.
Why would it be different? Because there are no write operations in between, so the data is the same.
So these are two concurrent write operations. And you have to, this is the picture you have to keep in mind. Okay, imagine 4 processes. I have 1 writing A, 2 writing B, 3 reading A, 4 reading A and B, and 4 reading also A and B. Now what may happen if you have a stupid distributed system, it says, it picks up this write, says, okay, let me propagate that to this one, but not yet this one, because in the meantime, A writes something, and that one is first then propagated to this one, then to number 4, and then later this B is propagated to 4. That's not supposed to happen.
So it's not the actual read operation, but the propagation of the read operation within the middleware.
The only conclusion that I can draw is if I have this scheme, then the distributed system did not maintain the same ordering of operations everywhere. Visibly, for P3 and P4, the ordering got screwed up. So this distributed system did not stick to the contract that it should provide sequential consistency. Is that clear? Not clear. So who is not clear? This is unclear. Okay. Tell you what, we're going to have a break. I'll come back to this just after the break. It's important that you understand what's going on here. If I lose you now, I'll lose you with the next scheme as well.